being shared right now, right?
Yep.
Awesome. So hi everyone, and thank you for joining us in week 5 of this machine learning bootcamp. I hope you've been learning a lot so far. So in today's session, we'll continue the talk on supervised machine learning models. And we're going to cover naive Bayes classifier, k nearest neighbors, and support vector machine models. Just a little bit about myself. Graduated from U of A with a computer science and specializing in bioinformatics. Currently, I work at ATB as a data scientist. I also joined the GGG community as a technical facilitator. For hobbies, I guess I like hiking, camping, and road biking. With some pictures, and I like to take pictures on the road as well. And I'm not a big fan of winter, so I don't mind it though for some short time though. Okay. So we'll start the session with an introduction, and then I will talk about naive Bayes, and then after that, probably gonna take a break, 5 minutes, and then Hayden will talk about support vector machines after that, and then I will continue with k nearest neighbors and final thoughts. As this is, I think, going to be the last session on the supervised machine learning models. Please, if you have questions, you can unmute or stop us at any time during the presentation. Or you could post on a chat or Slack, and we'll try to answer it when we find a chance. And yeah, I guess I'll start with an introduction. So we saw so far that supervised machine learning models rely on. Sorry, I don't know if I'm the only one who's hearing that, or. Sorry, I hear a lot of noise. I don't know if you guys can hear that.
Yeah, I can also hear a noise. Can everyone please mute?
Thank you so much. Okay, so we saw that supervised machine learning models learn by examples. So in the training set, so it can learn how to predict the labels on new previously unseen examples. On a high level, learn algorithm seeks the function of, say, G, where X is the input space and Y is the output space. So for instance, given n training examples, such that X at the ith index is the feature vector and Y would be its label at the same index. So we use a loss or cost function to measure how good our model is doing in predicting, which is basically beats the distance between the predicted output and the expected output. And of course, we use different loss functions depending on if the problem we are dealing with is classification or a regression problem. So for example, we use the mean square or MSE, also called quadratic loss in regression, and the cross entropy and likelihood in classification. So the loss measurement is used as a feedback signal to adjust the way the algorithm works. So many of these algorithms are probabilistic models, which you can take the form of a conditional probability. There are many factors to consider while choosing the algorithm of choice. So for example, naive Bayes and support vector machines are algorithms that are based on linear functions, whereas KNN is based on distance functions. So if each of the features make an independent contribution to the output, then these algorithms will perform really well. However, if this doesn't hold true, other complex models, such as neural networks or even decision trees, will perform much better. So the models we're going to cover today are used a lot as a baseline classifiers or models in many patterns or in many classification problems. SVM is a discriminative model, whereas naive Bayes and KNN are generative models. For example, the goal in discriminative process is to find the boundary that discriminates between the two classes from our data. Whereas in a generative process, we first pick the category for the record, and given the category, we generate the attribute values from the distribution of the category. And we assume conditional independence given a class. And we use the training data to learn the distribution of the values in a class. So for example, in order to classify a language of a document, you can either learn the two languages and find which is more likely to have generated the words you see, or learn the difference, what differentiates the two languages. Okay, so that's my introduction. Let's dive into naive Bayes, which is our first topic. So where does naive Bayes sits in the hierarchy? So it's a classification algorithm in machine learning, and it is included in supervised learning. So naive Bayes algorithm is based on the Bayes theorem or rule created by Thomas Bayes, which works on the principles of conditional probabilities. So this rule states that the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So yeah, this might sound a ramble, but bear with me. So because we're going to be deriving this formula shortly. So Bayes' rule is applied in many different fields, and is quite popular in machine learning in the field of natural language processing, or NLP. So before we get into the naive Bayes, we need to understand what conditional probabilities are and what is naive rule. For that, let's see why it's called naive. So naive because it assumes that all features or variables in our data that go into model train are independent of each other, which means that changing the value of one feature does not directly influence or change the value of any of the other features used in the algorithm. So for example, a fruit may be considered to be an apple if it is red, round, and about 2 inches in diameter, or 3. An naive-based classifier considers each of these features, red, round, and the diameter measure, to contribute independently to the probability that the fruit is an apple, regardless of any correlation between the features. Features, however, aren't always independent in real-world problems, which is often seen as a shortcoming of the naive Bayes algorithm. And this is why we call it naive. Okay, so let's start deriving Bayes rule here. So let's review probabilities. Then we can derive Bayes rule from conditional probabilities, or the definition of conditional probabilities. So assuming that this is our data set, containing 12 tweets overall. So 8 would be positive tweets, shown in green, and 4 are negative tweets, shown in red. And a tweet can either be positive or negative, but not both at the same time. So we want to look into a scenario, it's called the A, which is to calculate the probability of one certain event happening. So for that, we take the count of that specific event, and we divide by the sum of all events. So the sum of all probabilities has to equal to 1. So for example, to get the probability of a tweet being positive, we take the number of positive tweets, which is in this case 8, and we divide it by the total number of tweets, and that gives us 0.66. And the probability of a tweet being negative, then it's 1 minus 0.66, which is 0.24. So now let's look at a different scenario where we are looking to joint probability, where we want to compute the probability of 2 or more events happening at the same time. So here we're talking about 2 events that happen at the same time, say P of A and B, or the probability of B and A. So in our data set, it's like a tweet would be containing the word happy, and at the same time is positive tweet in our data set. I took this actually example of tweet from online, but I made these figures. So to do that probability, we look at the intersection of the overall events. In this case, in the table on the right, the thick lines or the boxes with the thick borders representing the tweet that contains the word happy. And this overlaps in two boxes with the positive tweets, and also two boxes with negative tweets. But we want to get the intersection of tweet that is positive and also contains the word happy. So we have 2 divided by the total number of tweets, and we get 0.1. So jump into the conditional probability. So according to Wikipedia, conditional probability is a measure of the probability of an event occurring, given that another event has already occurred. So now let's take a scenario C, where we want to compute the probability of one or more events that are happening given the occurrence of another event or another event. Say the probability of A given B, like in our case, like a tweet containing the word happy, given it is positive from our data set. To do that, we use the joint probability we saw previously. And so the probability if a tweet is positive, given that it contains the word happy, is equal to the joint probability of these 2 events divided by the probability of a tweet containing the word happy. So notice here, basically, instead of looking into the entire corpus of tweets, we only look at the tweets that contain the word happy, because we know happy, it is given. So we end up with 2, which is the number of tweets that are positive and contain the word happy in this table on the right. And that divided by 4, which is the number of tweets containing the word happy, and we get 0.5, which means that our tweet has a 50% likelihood of being positive if it contains the word happy. So we could also do this for positive tweets, and we get a 25% likelihood of having the word happy in our tweet, given it is positive. So note here that the conditional probability is not symmetrical. So for example, saying that probability of A given B does not equal to the probability of B given A, but the joint probability that we talked about earlier is symmetrical. So saying the intersection between A and B is the same as saying the intersection between B and A. So now you could probably see where this is going to. Overall, we can see here that deriving the probabilities in this way would be a problem if our corpus or our data is huge and we have multiple events happening, meaning that our joint probability will become challenging to compute, which is usually true most of the time. So using the example so far, we have saw the following 2 equations. So now let's take a closer look. If we take a closer look to these 2 equations, we could derive actually Bayes' rule. So knowing that the intersection highlighted in gray is represent the same quantity, no matter which way it's written. So we can remove it from the equation, and with a little bit of manipulation, of course, we could arrive to the Bayes' rule, which is the already expression of Bayes' rule based on our example here at the bottom. So this equation basically states that the probability of a tweet is positive, given that it contains the word happy, is equal to the probability of a tweet containing the word happy, given it is positive, multiplied by the probability of positive tweets over the probability of a tweet that contains the word happy. So in other words, Bayes' rule is a way of calculating conditional probability without actually joint probability. Okay, awesome. So we just derived Bayes' rule basically from the expressions of conditional probability. So the main takeaway for now is Bayes' rule is based on the mathematical formulation of conditional probability. And with Bayes' rule, we can calculate the probability of x given y if we already know the probability of y given x and the ratio of the probabilities of x and y. So the terms here in Bayes' theorem equation are given names and depending on the context where the equations are used or the equation is used. The probability of x given y, it's called a posterior probability. So it's probability of x given value of y. And the probability of y given x is called likelihood of y given x is true. And then Px is the prior probability of event x, and Py would be the evidence in this case. So it would be the probability of event y. So it might not be helpful, but like that, but we'll see an example in a second. Next slide, maybe it could help out. But if we think about the calculation from these different perspectives, it could help us map out actually our problem into the equation.
Hassan, do you mind if I ask a question?
Yes, go ahead.
So why sometimes we call it probability and sometimes we call that likelihood?
These naming are like, when I looked at, actually I might have looked specifically into each one why we call them this way. And the probability, or saying that, because we try to get the posterior probability here, saying that the inverse in that, saying the probability of y given x, if we want to look up for the posterior probability, it becomes or we could call it as a likelihood. I don't know if there's a better explanation for that.
Yeah, okay. Yeah, I think, yeah. Probably they probably mean similar in certain conditions, but yeah.
Yeah. I think this confusion, this is why I put the next slide, I think might clear things up. And so we could look at it with clearly with the smoke and fire case. So say like trying to find the probability of a fire, given that we have smoke. So we call the fire, the probability of having a fire is the prior. The probability of having smoke, given that we have fire, would be the likelihood, and the probability of smoke would be the evidence. So this would be our equation. So I put this here, for this purpose, trying to like see if that clears things up, basically. Anyways, okay. So question alert. We have. I just put this question, and I'll just give like a few seconds. I might need to open the chat just to see your answers. So, just what is the probability? Just to make sure like this went through. What is the probability that the sentence "Machine Learning Bootcamp is awesome" is positive? Given that the 40% of positive tweets contain the word "awesome," a total of 30% of the tweets contain the word "awesome," and 60% of the total number of tweets are positive. So I'll just give a few seconds here. I'm just going to open the chat. I think I just gave the answer. I don't know why the chat is not. There you go. Finally. So you could put your answer in the chat just to see. If I see one answer or a couple, I'll continue basic. This would be our equation. yeah, I think I'm just going to continue. I didn't see answers, but the correct answer here would be 0.8. So basically, according to this, if we just plug in the values, it becomes 40 times 60 over 30, basically. Okay. So now we want to construct the classifier. And so we saw that Bayes' rule provides a formula for the probability of y given x. But in real world problems, we typically have multiple x variables. So multiple features, basically. When the features are independent, we can extend the Bayes' rule to what is called naive Bayes. So the approach in this case is to compute the posterior probability for all values of C using the Bayes' rule. And choosing the value of C that is the maximum, which is equivalent of saying that we want the value of C that maximizes the likelihood multiplied by the prior probability of the probability of C. This is because the denominator does not depend on C, and the values of the features A from I to, say, K, number of features are given. So the denominator is effectively constant. So how do we estimate the likelihood? Well, if you remember, we're acting naive now, so we assume independence among the attributes when the class C is given. So we can estimate the likelihood probability for all values of C, of A and C. So this means that under the previous independence assumption, the conditional distribution over the class variable C is the derived feature dependence model. And where evidence Z equals to Px, which is the scaling factor dependent only on x from 1 to x to n, the number of features. There is a constant, and if the values of the feature values are known. So next. So finally, the naive Bayes classifier is basically a combination of the previous model, which is the derived independence feature model, with a decision rule. So the rule is to pick the hypothesis that is most probable, which is known as the maximum posteriori or MAP decision rule. And we end up with a function here that assigns a class label, say y hat, and for some k, where k is possible outcomes or classes. So the argmax here is basically the operation that finds the argument that gives the maximum value from a target function. So this equation means that for a new point x, it is classified to class C at k if it is the maximum over all possible values of C from 1 to k. Perfect. So our classifier is now built, but creating a naive Bayes classifier essentially means that we need to compute counts. So you may have noticed or realized by now that we have a couple of problems. So if one of the conditional probability is equal to 0, then this would lead to an entire expression to become 0. So this could happen when an instance in test data has a category that was not present basically in the training. So what do we do in this case? How do we handle such missing classes? So in this case, in this example, we could see here that this is an example basically of spam and ham emails. So we want to classify emails that are coming in if they are spam or not spam. So here it just probability is computed of having a spam email or not. And then here we do two probabilities of the word in each two category. So we get the unique words and we do the count of the words. And we divide this by the total number of the words. So this is what the probability of word in each table is. And we could see here that if we got this new email that contains these words, and Office is one of them, but we saw Office in not spam emails or ham emails, and we got a probability out, but we didn't see it in the training. We don't have it here, so it's actually 0. So our whole expression becomes 0. So how do we handle this basically? So it's easy to handle. So to avoid this probability being 0, we perform something called Laplace smoothing, which is also referred to as additive smoothing, I think, or Lidstone, I think it's more general form of it. So this technique is used to smooth categorical data. So smoothing the probability function means that you're actually going to use a slightly different formula from the original. So note that in the new formula, so we add 1 in the numerator. So this little transformation avoids the probability being 0. But this means that we add a new term to all the frequencies that is not correct, normalized by the n class. So to account for this, we will add a new term in the denominator, n at I, and that will be the number of attributes values for attribute A at I to account for the extra term added in the numerator. So now all the probabilities in each column will sum to 1. So looking at our example again, we can see by doing this, we don't have any 0 probabilities. So most naive-based model implementation accept this or an equivalent form of correction as a parameter. So here I'm just putting an example again how we calculated this. So we add 1 to the numerator when we want to do smoothing, and then basically here the new count. So we have a different count than this one. So how we got to this probability 0.241935 is we do 60 divided by 243, which is the total number count plus 5, because we have 5 unique words in this case. So now we get a probability of the email being spam, and because it's higher than probability of it being just regular email. Okay, so we solved that problem, but we have this problem, which you might have assumed as well or realized. It's called the vanishing value problem, or at least I call it that. And it happens when conditional probability involves multiplication of many very small numbers between 0 and 1. So in this case, the value becomes really close to 0 and might lead to numerical underflow. So the trick is to compute this, to fix this, is to use the logarithm of the conditional probability. So remember that the formula we are using to calculate a score for our naive base is the prior multiplied by the likelihood. So the trick here is to use the log of the score instead of the raw score. So this allows us to basically write the previous expression as the sum of the log prior and the log likelihood. Okay. Now that we got these issues out of the way, let's discuss how we handle continuous data when applying naive Bayes to a classifier. So it's solvable. And we saw that naive Bayes classifier performs very well in case of if we have categorical data, or at least doesn't have a problem with it. But how do we perform this classification when we have our data continuous? So for example, if we have something like temperature, height, and so on. So there are 2 ways. The one way is to discretize each continuous attribute, and then we replace it with the continuous attribute value with its corresponding discrete interval. And then another way of doing it is by assuming a certain form of probability distribution. And we assume a certain form of the probability distribution for the continuous variable, and we estimate the parameter of the distribution using the trained data. So a Gaussian distribution is usually chosen to represent this class, the class of the conditional probability for continuous attributes. And the distribution is characterized by two parameters, its mean and variance. So here where mu and sigma are the mean and variance for the continuous variable x computed for a given class C. So yeah, don't worry, we don't have to do this if you want to build such classifiers. We're going to see in a second that we can just use different naive-based classifiers depending on our situation. And if you want, there are all ways to make the feature more near normal in the data set if you want to improve the model accuracy. But we're not going to go through this today. Okay, so overall, naive-based classifiers are a family of simple probabilistic classifiers based on the applying Bayes theorem that we saw with a strong naive independence assumption between the features. So there are different types of naive-based classifiers that we could use. And those are the following, but not limited to. So we use a multinomial naive Bayes for if we have discrete data. And this is mostly used for document classification problem. And whether a document, for example, whether a document belongs to the category of sports, politics, technology, the feature or predictor used by a classifier, or the frequency of the words present in the document. The Bernoulli naive Bayes is similar to the multinomial naive Bayes, but the predictor or the parameters that we use to predict the class variable are Boolean binary variables, such that they take only two values. For example, yes or no, or if a word occurs in a text or not. And lastly, here on the list, the Gaussian naive Bayes, and we use it for when all our features are continuous. And for example, in the Irish data set, features would be our sepal width, petal width, or sepal length and petal length. So its features can have different values in data set, as width and length can vary. And we can't represent features in terms of their clearances. So this means data is continuous, and we use this naive-based classifier for that. Okay, so let's go look into the notebook that I shared earlier with you. Sorry, if there's any question, you could unmute and ask now too. Sorry, am I still sharing here? Did I lose my screen?
Yeah, we can see your notebook.
Okay, cool. Thanks. Oh, I want to exit this. There we go. Okay, so we're going to go over two examples of Bayesian classification. One is Gaussian naive Bayes, and we're going to see the next one would be multinomial naive Bayes on two different examples. So here in this case, we just create just random points on this in this Gaussian naive Bayes, so it's normal distribution, and we scatter them on this plot. Now we could see we can just basically, if we draw a line, we could distinguish between these two classes. So yeah, one fast way of creating a model here is we assume that data is from a normal distribution with no covariance between the dimensions. And we could fit this model simply by finding the mean and standard deviation between the points within each label. And this is a result showing this this assumption, the naive assumption. And these two loops, they represent the models. So with larger probability toward the center of the ellipse. So the more we are close to the center here of the ellipse, the more we the higher the probability of that class being, that record being that class. So basically, this is our training data we created. And here, basically, we want to test this model. So we basically, here in Python, we imported this model, Gaussian and naive Bayes from sklearn. And we initialize, make an instance of it, and we fit X and Y that we created above here. We want to create a test instead, and we create a random test set, and we basically here we're multiplying X by 14 and Y by 18, and we add to X each time -6, and on Y -14, and we predict the X new using the model that we created above, and we plot the results. So you could see here the model has, based on this plot, it was able to significantly perform very well. Here, basically, we laid the training data above the data that we just created to test the model. It was able to classify it perfectly. So the good thing is, in this model is, it allows for probabilistic classification. So we could commute, or we could call the predict probability function, and we could see how it's actually, it tells us which class, which record belongs to which class. So I printed the last 8 records here, and showing that in our this data, basically, we had X -5.44, for example, and we had Y was -4.8, so that's our point. And then when we print the probabilities, we could see that the classifier told us that it belongs to the one class, or the probability that belongs to that one class, it's 89% versus 11%. And actually, if we want to maybe look it up and see where this point belongs on the graph, so -5, about here, so 4, -4, and 8. So maybe something like here, I would say, or here. You could see here a lot of the probabilities for other points would be 100% steered toward other class. Yeah, I think this was a really simple explanation of, or example for the Gaussian naive Bayes. And looking into the multinomial, so we basically use this for, as we mentioned previously, if we have categorical features or data. And here, what we do is we use sklearn again to, however, this time we fetch 20 news groups, and this would be the target names. So basically, we want to classify if a new, let's say, a new text coming in, we want to classify which group belongs to from this list. So this is our data target names, and here I think we just pick in this example 3, 1, 2, or 4 target names of these, and we split basically our data for training test. And this is just an example, printed example from our news groups, showing like how the text looks like. It's always good to look at your data. So yeah, we do vectorization. We convert strings to vector of numbers, and these are, and this is where we fit the model here. So we actually, for that, we make a pipeline, because what we did is, vectorized our data so the model can understand. And then we, in this pipeline, we throw in the data vectorized and the model that we instantiated. And we fit the model on this data, the train and target, the X and Y, basically. So here we do the prediction. And in order to evaluate our model, one way of doing that is we could import the confusion matrix, and this is built in as well in sklearn. So this is basically like our confusion matrix here. As I mentioned, they took the 4 target names from this corpus, and we could see here that how our model performed. So it was able. There is also, you could print also there's other outputs you could print, and it tells you how many examples, where you could get from here actually. So basically in our, let's see here, in our data set, for example, for socials, religion, Christian, we had 392 plus 5 plus 1, that's 6, 398 basically data points, or if you may, and it was able to predict most of them correctly. So basically the true label and the predict label here. So it seems like the model is not very well, actually didn't perform real well, but according to be honest, I would just print. I'm just gonna try to print some. Oh, okay, sorry. I think I need to run this from the beginning. But if we want to evaluate the model ourselves, so we could actually try it here, and we could just, if we make this function and we use the model that we just trained, we could actually send in a sentence, and it's gonna what's gonna do is gonna vectorize it, and then it's gonna spit out which group it belongs to. For example, send in a payload to the ISS, International Space Station, so it predicts this as science or belongs to a space group article. And here is another thing about discussing Islam versus atheism, and then it belongs to religion and Christian and so on. Okay, so basically these are the examples, pretty simple, and we use naive Bayes a lot as a baseline. Just gonna go to the slides. Present again. Oops. There they are. Okay, so it might have been going slower than I thought. So just to end the naive Bayes now, and we're just going to talk about advantages and disadvantages before we end it. So the disadvantage of naive Bayes is basically simple to implement, and only in most cases only probabilities that we need to calculate, and it performs better than other models on a small data set. It is not sensitive to irrelevant features, since each feature has the same weight. Can be used for both continuous and discrete features, and can be used for binary or multi-class problems. So it works well with high dimensions. For example, in text classification, we see this a lot in NLP. This is because as the dimensions of the data set grow, it is less likely for any 2 points to be found close together. So this means that clusters in high dimensions tend to be more separated on average than clusters in low dimensions. So for this reason, simplistic classifiers like naive Bayes tend to work as well, or even better than more complicated classifiers on high dimensional data. And these are some of the disadvantages. So it assumes basically, that's a big disadvantage, assumes all our features are independent, which is not always the case. And if it holds false, it basically, this model will perform really poorly. But we could solve this by performing basically some analysis on our data and find the features that are correlated, for example. And then what we do is we would just select the features that are uncorrelated, and we train the model with that. But keep in mind that also, although you do lose the ability to basically exploit the interactions between the features, but for classification tests, this often isn't a problem. So you could always use other techniques such as, for example, Bayesian belief networks to preserve known conditional dependencies between the random variables and the conditional independence in all other cases. So you can look that up, because I actually I don't know how that works. So the disadvantage also that it treats all attributes equally, but we know that some weights, some attributes have been weighted more than the other ones. But some weights in naive, some weights can be added to the important attribute to increase their contribution in the final decision. And we saw that there is a problem, or a couple of problems, which is the vanishing values when we multiply multiple small numbers between 0 and 1. And we saw how we could solve that, as well as the zero probability problem. And we also saw how we could solve that. Yeah, if we have continuous data, we could always also solve it by discretizing the continuous data. And finally, we trended applications for naive Bayes. It's used a lot in NLP tasks, sentiment analysis, spam filtering, or even like in medicine, in medical field, where you want to detect, like for example, here I put disease detection based on genome-wide data, and then in image classification, for example, in face recognition. Okay, I think that's it from me on naive Bayes, and I think it's time probably to go for a 5 minutes break, and then we will come back in 5 minutes, 1:55.
Hassan, there's one question in the chat.
Okay, just one second.
So the question, how to use for the multi-class problem?
So one second, I'm just gonna. So if we have a multi-class problem, we could basically, I think I'm gonna look into this problem. No, not this one. If we have a multi-class problem, we're basically gonna have to sorry. I believe, is this, I saw also another question. I just opened the chat. I don't know if that's a question, it's a long one. Oh, anyways, so if we wanna use a naive Bayes for multi-class, I would suggest basically to depend on this classifier for binary. However, it's possible to do multi-class. But I don't know on top of the head how you would basically use these functions to compute that, because it's gonna depend on multiple things here. And I don't think I have even used it for multi-class classification. But I would jump to use, for example, something like we're gonna talk about soon, which is SVM, or some other class, and that could even perform better, I would say. Decision trees that we talked about earlier, but I don't know on top of my head how I could use this in multi-class problems.
So Hassan, maybe I was wrong, but in your example, in the collab example, in that text classification, is that a multi-class or just binary classification? In your collab example, when you use a multi-nominal naive Bayes.
So what's the question in terms of like regression or?
No,
Sorry.
so in your example, I think in your last example,
Right,
it's
right.
you
This one.
use the multi
Yeah,
nominal.
like we have a categorical data here, and you could use the multinomial for a categorical data, right? So we have, so
in
it's
this
we have multiple target
categorical-
names basically. So we have different classes of multiple classes here in terms of categorical data that we could include in our training.
So this can be applied for the multi-class problem.
We could apply this for a multi-class problem actually. Yeah. I think I actually. Yeah, like usually it's used in of course categorical, but mostly in binary classification, which would be this in this case. But yeah.
Yeah, I think I kind of agree because in multi-class you can the typical way is just to use is one against multiple, so you can classify one categorical versus the rest of them, and then you keep classifying the rest, just one against more. I think there's one strategy you can apply.
Right. Yeah. Yeah. So if you apply the multinomial naive Bayes, that's your best would be your best classifier for your categorical data, and I would use other models for multi-class. They're probably going to perform better, but you probably could use this, and it will give you the. I didn't show like comparison between this but you could use this as a baseline.
Yeah. And do you want to take the other questions in the chat? I can
Yeah,
repeat those questions.
I actually see it, but did I miss? There was a question before, or is this just?
Yeah, so like Matt asked about if you were to apply the same Bayes method, but for dependent features, would the algorithm scale exponentially?
That's a good question. If you have dependent features, I won't even try to apply this model basically from the get-go. How they would scale? I don't know actually. I don't know how this would scale because your features are independent, and this model assumes independence between features. So I'm not sure how this would scale.
Yeah, and maybe there's another question about like how do you apply the classifier several times, like A versus not A and B, or I think he's asking about one against more strategy, like basically dealing with multi-class classification problem.
Right. Yeah.
Yeah. But yeah, I think basically, John, you're right. You can just apply this several times, and then you can. That's a very common strategy to deal with multi-classification problems.
Yeah, that's correct. Okay, I think that's all the questions, or?
Yeah, that's all the questions. And yeah, if you want to take a break, we can take about 5-minute break.
Okay, sounds good. So we'll be back to 2.
Yeah, sounds good.
Okay, thanks.
Hey, if everyone is back, I will begin. I will share my screen here. So can everyone see my screen here and hear me clearly?
Yep.
Perfect. So hello, everyone. I hope everyone is enjoying the lecture so far. Basically, I signed up to help out with week 5 supervised learning. So I'm one of the participant volunteers. And my name is Hayden Figi. I am currently a data science and analytics engineer in training with Husky Energy. My educational background is petroleum engineering. I studied at the University of Regina and graduated in 2018. After graduating, I've held several engineering roles at Husky. And prior to starting my current data science role 5 months ago, I held more traditional petroleum engineering roles, production, development, planning, operations, etc. So I would say I'm pretty new to all of this. And I'm here today to speak to you about support vector machines, or SVM. And I really hope you guys can learn something, and I hope you find this topic as exciting as I do. And also, before I begin, I would just like to do a quick Movember plug. So I normally don't have a mustache, but right now I'm starting to grow one. And I am doing this for No Shave November. Myself and some colleagues are raising money for men's health, mainly prostate cancer and mental health awareness. Last year we raised $1,700, and this year we're hoping to do better. So if any of you are looking for more information about Movember or looking to donate, please reach out to me on Slack or LinkedIn. So I will change the slide here. So to start with, I'm not an expert in machine learning or SVM. And in fact, my motivation to volunteer today was to actually learn SVM. And as the famous Richard Feynman once said, if you want to master something, teach it. So I'm far from mastering SVM, but I have learned a lot through preparing for this. And I hope I can spread some of that knowledge with you guys today. So what is SVM? SVM, or support vector machines, is a powerful and versatile machine learning model developed by Vladimir Vapnik and colleagues in 1992, 1993, and 1997, as they continually iterated on the topic. And unlike the previous model we discussed, naive Bayes, this is a relatively new subject. And in fact, Vapnik is only 83. And also, unlike the past topic, this is not a probabilistic model. So to start with, SVM is a very broad subject. It covers a lot of different areas. The model itself can be used for linear and non-linear classification and regression problems. It can be used for outlier detection, and even for some unsupervised model or methods such as clustering. So as this is such a deep topic, I'm going to really just focus in here on classification and touch a little bit on regression. I'm also going to focus on the application side of things. I'm not going to go too deep in the math. However, if you are wanting to go into the math, and I would encourage you to, you can go on YouTube and search MIT OpenCourseWare. They have a great lecture on it. Also, Andrew Nang has a pretty good lectures on this as well as part of his ML course. And also, as always, if anyone has any questions, just post in the chat. I'll be checking there frequently, and also feel free to just open up that mic and ask away. So on the next slide here, similar to what we previously looked at, this is breaking down where SVM fits in machine learning. So I'm just going to focus here on the classification and regression. And for SVM, this can be done as part of supervised learning. And if you want to learn about more of the different applications outside of classification and regression, I would recommend reading some of Vapnik's papers or other resources online. So here we start with SVM classification. So this is the most used SVM method by far. And because our linear binary classification is the simplest, I'm going to start here. So the goal of our linear SVM models is to find a hyperplane that separates the two classes and provides the largest margin between them. So for a very simple case like we have here with our red squares and our blue circles, we probably could eyeball a separation. And I've actually done that here with this dotted line. So we can see that this dotted line is probably one of the best fit lines to separate these two classes. However, I don't know if it's perfect. And also, I'm not sure how to do this in higher dimensions, like if it was 5 dimensions or 1,000 dimensions. So that's really where SVM comes in. And here is an SVM model that has fit the largest possible margin or the largest possible road. And really all that is the separation between the classes. So we can see here that we have a margin, and on the edges of the margin, we have what's referred to as support vectors. And another, or a really important thing to talk about here is that these support vectors are really what drives this optimization problem and the selection of the optimal hyperplane. So we could actually remove any of these non-filled in shapes here, and it wouldn't impact our optimal hyperplane. And with that said, we also could add many more shapes outside of the margin, and it would not impact our hyperplane. So this actually helps with computational efficiency because we're only looking at a very small subset of the data, in this case, 3 points. So before we get further in, I just want to review what a hyperplane is. So we're all on level playing fields here. So as we learned in geometry, hyperplane is a subspace whose dimension is 1 less than that of its ambient space. So for our previous 2D example, a hyperplane is simply a 1D line. And then for a 3D example, we simply have a 2-dimensional plane. And this continues on and on into much higher dimensions, which is important because for SVM, we are often looking at very high dimensions, sometimes in 1,000+ dimensions if we have 1,000+ features. Also, as part of this quick review, I want to highlight this equation here, hyperplane equation from linear algebra. So from linear algebra, we know that the equation of a hyperplane is W dot product X plus B equal to 0, where W is a vector normal to our hyperplane and B is some offset. And then this is very similar to the equation of a line, Y equals MX plus B equals 0, or sorry, Y equals MX plus B. And thus that can serve as kind of a memory tool to keep this equation in mind. So here, again, we're looking at this linear SVM. We can see that we've maximized the margin. And I'm going to start introducing some key concepts here. The first is we have data that is separated between negative and positive cases. So in here, we have blue is positive and our green is negative. And we also have the equations of our hyperplanes on this line here, or sorry, on this plot. And we've also now defined the maximum possible hyperplane as 2 over the magnitude of W. And I don't mean to lose everybody. I just wanted to show basically where we want to get to in the next 2 slides. And we're going to derive how we find out the equation for maximizing this, this margin, because this is very important for the math behind SVM and the maximization and minimization problems that we must solve to come up with our hyperplane. So here we can see in this photo that we have positive and negative data. So we have positive cases over here and negative over here. And we also have 2 support vectors in red. So these are these vectors here and here coming from the origin. We also have this weight vector in gray and this W. And from here, we also could see that the maximum margin would be the distance between these two hyperplanes, the positive and negative hyperplane. And sorry, just one second. So if we sub in the previous equations for the hyperplane we looked at into this maximum margin equation, we can actually define what the maximum margin would be. So here I have displayed some of the math here. I'm not going to go through it in too much detail, but we can see that the hyperplanes equations are simply W transpose X plus B equal -1 and W transpose X plus B equal -1. And we remember that this is simply the same as the dot product version we previously saw, just a different form of it. And here we can see that if we take the difference between these two equations to just find this, this distance between the margin, we can thus find the maximum margin equation. So by solving algebraically, we come up with 2 over the magnitude of W. And this is if we want to maximize the margin. We could also change this to a minimization problem if we look at minimizing the magnitude of our W here. So that's the exact same thing as W was in the denominator. Alternatively, we also could introduce this 1/2 and this square term, and it would be mathematically equivalent. And if you're a little confused why we would do that, don't worry, I was too. But basically, it's just like a mathematical convenience for some of the Laplace transforms and some of the more kind of advanced mathematics that go into solving this minimization problem. I don't really want to focus in on there, and I'm going to save us all the pain of going through that math. But if you want to kind of go through that in detail, like I said, there's tons of online sources. I just really don't have the time here. So I hope I'm not going too fast here. And I don't know if I can see any questions. So if anyone has any questions, just let me know. So now we've found ourselves at the SVM objective function. So we just came up with this first term. And here simply this W transpose W is the exact same thing as that magnitude of W we previously looked at. Mathematics loves changing the forms of equations. So I hope I didn't lose anyone there. And then we see this new term introduced, which is our hinge loss, which is our loss function. So basically, hinge loss is a type of loss function that's used in classification problems. And what it does is it leaves correctly classified terms out of the loss function. So that means that we are only penalizing incorrectly classified points based on their distance from the boundary. And this really is why the support vectors and misclassified terms are the only ones that are impacting our optimal hyperplane. As we previously saw, we can remove some of those properly classified points that are outside the margin, and it won't impact our optimization, which is it's interesting. And I'll go through that a little bit more in detail in the notebook. Also, what has been introduced here that I really want to focus on is this hyperparameter. Hyperparameter C is very important for SVM. And basically what it does is it controls our trade-off between a large margin and then a small loss. So we'll see in the next slide how this looks in a practical sense and how it relates to overfitting and underfitting and the bias variance trade-off. And also, I would just like to quickly mention that our minimization or our objective function here is convex. So we can use quadratic programming and other math to basically determine the global minimum. So this is like a final solution. We don't have to worry about local minimums as we did with some other ML models. So now we have our C hyperparameter. So we can see in our diagram that we have some linearly separable data. We have on the left these circles and then these X's. It really doesn't matter what it is for this demonstration. I just want to show you that when we have a large C, we are really penalizing the misclassifications, and we are basically prioritizing classifying everything right over maximizing that margin. So as a result, we end up with a very small margin here. You can see the distance between these circles and the X's is very small. And what this does really is it leads to lower bias and higher variance, which leaves us with a model more prone to overfitting. And in the opposite case, when we have a low C value, what it does is it allows for some misclassification with the goal of maximizing the margin. So we can see here that we actually classified, we have a misclassification here. However, it has resulted in a larger margin, which offers higher bias and lower variance, and we can be prone to underfitting if we have a very, very low C value. And as with any ML model, really what we're trying to do is find the balance here between overfitting and underfitting. And ideally, we're searching for that low bias, low variance. And before I move on, does anyone have any questions here? To be honest, I don't even know how to view the questions. So if there's any questions, just speak up, Lay.
Yeah, sounds good. There's no questions so far.
Perfect. Here I have a question for you guys. So based on the SVM principles that I've introduced, how do we think that the proper classification of this data is? So now we have this red data class and this blue data class, and they're in these circular patterns. So it's not necessarily linearly separable. So do people think it's A, this horizontal line, or sorry, this diagonal line? Do we think it's B, this horizontal line here? Or do we think it's C, this circular line? I'll just give everybody a second to submit their answers. So yeah, unfortunately, I didn't really research how to like find out what the chat is. So can you just let me know there, Lay, if anybody's answered? And if not, I can provide the answer.
Yeah, the chat today is pretty quiet, but yeah, you can go ahead with the answers.
Okay, perfect. So this was kind of like a trick question in a sense. So the answer is C. However, if you really only like focused on the principles that I've shown so far, you might land upon like an A or a B. I think B would be like a good linear separation. However, we can use the principles of SVM to separate non-linearly separable data with linear hyperplanes. So that sounds kind of strange, and I'll show you how that works. Essentially, we need a bit of math and some tricks. So we have some tricks up our sleeves that can help us. But in simple terms, we can see that if we add some Z value, so we have some function that transforms the data, how it does that is not very important at this point. Just think that there's some function, let's call it theta, that introduces a new term and allows us to separate the data in 3 dimensions. So if we looked here, we could probably visualize maybe 0.5, a 2D plane could separate the data. And what we need to do is actually apply some function, theta, and then have our separating plane, and then reverse our function and bring it back to our original dimensions. So we have some mapping function, we take our data to a higher dimension, and then we bring it back to our original dimension. So with a 2D dimension or a 2D example, we bring it up to 3D, and then we bring it back to 2D. And really, we could do this with any function. Maybe for some other data, we could square our x1 and x2 and take the sum. However, with SVM, what we really want to do is apply a kernel function, because there's some mathematical advantages to that I'll discuss next that will allow it to work for any data, and it will also be more computationally effective. So next, the kernel trick. So we previously saw how using a function like a kernel can transform our data to a higher dimension and allow us to use the SVM principles previously discussed to maximize the margin between classes. So what is a kernel trick? So to start with, this is a scientific term with the word trick in it, which basically means some strange and complicated stuff is going to happen, because you don't see trick too often used in science. So I find that pretty exciting. And basically what this trick does is it allows us to map linear learning algorithms to nonlinear data using these kernel functions. And there is actually a strict definition for what a kernel function is. And this is provided by Mercer's theorem. I'm not going to go into the details of that, but just know that you can create your own kernel function as long as it abides by these rules. In practicality, you're likely going to use some of the provided kernel functions that sklearn has, or some other SVM package, but it's just important to note that. And lastly, and most importantly, these functions all employ mathematical tricks that allow us to operate in a higher dimension without ever computing the coordinates of the data in that space. So essentially, this means that we can do these transformations very computationally effective compared to, say, just plugging in some random function. So what are some of the kernel types available in sklearn? So there's the polynomial, the RBF, or the sigmoid. So I'm gonna really focus in on just two of these, the polynomial and then the radial basis function, the Gaussian radial basis function. But I just wanted to talk a little bit, very high level, what these functions are doing. And essentially what they do is they take two data points and they calculate a distance score. So this score is higher for closer data points and lower for further away data points. And using this score helps us to transform the data points to a higher dimensional mapping, which reduces the computational effort and time, especially for huge amounts of data. And it prevents the need for a more complex transformation. It also ensures that the data, no matter like if it's centered or not centered, it's going to be mapped as we would expect, and it's going to allow us to have separable data. So next I'm going to go into, I'm just going to review the types of kernels that are often used in sklearn and in SVM in general. So these are the polynomial and the radial basis function, and then the linear function. So it's important to note sklearn refers to linear as a type of kernel. However, a linear kernel is really like no kernel. It's just kind of something you got to know for applying these. And the linear is going to act exactly as we have just went over in the linear cases that I showed us. So we're just going to maximize that margin. And we would apply that to linearly separable data. And then these other kernel functions, our poly and our RBF, can be used in both linearly separable data and non-linearly separable data. So in this example here, we have linearly separable data, red and green circles, but we can just see that these different kernels provide like different shapes of lines, which could allow us to fit different data types more effectively or less effectively than, say, a linear. And I believe that the most commonly used, and actually the default of for SVM, is the Gaussian RBF. So I'm going to go over that next. So here's an example of the Gaussian radial basis function. And I'm not going to go into the details in the math, but here's the equation. And here's also how it looks mapped in 3 dimensions. And we can see that we have our data on the z going from 0 to 1, the values. And then this is that closeness score that I discussed. And we can also see that we now have this gamma. So gamma is one of the few hyperparameters available within SVM. And on this next slide, you'll see basically what that gamma does. So I'm a very visual guy, so I'm just going to show you visually. So we can see here that as gamma increases from 0.5 to 12.5, basically this hump or the bump, I don't know the technical term, becomes narrower. And likewise, as it becomes smaller, it becomes wider. And this is just going to change how the data fits. For me, seeing this in 2D makes a lot more sense. So we can see how our decision boundaries are impacted. Like I said, as we increase gamma, we become less rigid. So we can really see that the decision boundaries starting to fit towards the data a lot tighter. And this can lead to overfitting if we have like a very high gamma, and likewise underfitting if we have a low gamma. But when optimizing an RBF or any SVM, we need to really balance our C hyperparameter and gamma in the sense that we can't just say, hey, our data is overfitting, let's lower our gamma. That's not necessarily true. You got to look at this holistically and optimize the C and gamma simultaneously. I hope that makes sense. Next, we have our polynomial kernel. So people are probably more familiar with polynomial functions. And we can see here in 2D that like as we increase the degree of our polynomial, D here, that essentially the line or the boundary becomes more complex. So we could generalize and say as we increase D, we could tend towards overfitting, as we've seen in many other ML models that employ polynomials. And again, I just want to quickly show this 3D picture to show you how our 3D kernel mapping changes as we increase our dimensions. So we can see we like have a different shape. It's a little bit more narrow as we have a higher dimension. And yeah, I just wanted to say that like, depending on your data, these different kernels might fit better. So when you're like cross-validating your model and you're training, likely you're going to want to try with like, say, linear, you're going to try polynomial, RBF, maybe sigmoid. And that's kind of like up to your discretion. And is there any questions thus far before I get into multi-class SVM? Because so far we've only looked at like binary. Is it positive or negative classes?
There's no questions in the chat.
Okay, thank you. So in a real world application, it's like very common to have non-binary classification problems. So how would we fit an SVM here? Because SVM is inherently binary. So if I put like a line here, it's not going to mean anything because we actually need to employ multiple SVMs. And this is something that's already kind of been alluded to in some of the questions related to the naive Bayesian. And I'm going to show you the one versus all and one versus one methods that are employed here in SVM. And they also can be employed in other ML models. However, I believe SVM is like one of the stronger classifications for multi-class data, as Hassan mentioned. So when there are more than 2 classes, instead of creating a single SVM model, we actually make multiple models. And we basically let them fight it out, and they each predict the most likely class, and we take the best result. So there's basically 2 ways to do this. The one versus all, or it's also called the one versus rest approach, is that we create as many SVM models as there are classes. So in this case, there's 3 classes, purple, yellow, and then let's call it cayenne. And then basically we have a model that will determine, hey, let's separate purple from the rest. So the purple from all of them, and then yellow from all of them, and then green from all of them. And what it does when we have new unseen data, the models will then each try and pick the correct side, and whatever the correct side is, then it will be classified there. So for example, if we're looking at this purple model and we have new data in where my cursor is, or here, I'll do a pointer right here. Well, that's going to be the purple classification. And then basically whatever was assigned the most common class, then that's what it's going to be considered in our one versus all method. And then in our one versus one approach, basically what we do is we create an SVM model for every pair of classes, and each SVM model will describe a hyperplane that best separates one class from another class. So in this case, we now have purple and yellow, and we have a hyperplane that separates them. And it's just using the same principles we talked about, in this case, the linear SVM hard margin. And then in this case, if we're looking at our green and yellow, we have another line. And essentially what happens here is when we have new unseen data, we will look at it in all the different models, and every time we basically guess that it's towards one class, then there's like a vote towards that class. And then at the end, we look at whatever model had the most votes, and that's likely the one that it's going to be. So again, if we had a point here and we're looking at the yellow versus purple, well, this is purple. And then if we look at our green versus purple, this is also purple. So 2 votes for purple, this is purple, or likely purple. And again, this is not probabilistic. So one thing that like somebody may have noticed is like there's this big triangle in the middle, and likewise there's like a smaller triangle here with 1 versus 1. So how would we approach classifying data that falls within that triangle? And the answer is that there's a new formula for that, or a new method. And what we actually do is something that's called Platt scaling. And what it does is essentially takes the distance of the cases from each hyperplane and then uses logistic functions to calculate probabilities of what class it's going to be. And I'm not going to really go into the details here of how that works, but I just like really wanted people to know that there is cases where this isn't going to just straight up identify a class, and we have to look into like a probabilistic model to help assist our SVM. And also I think it's important for everyone to know the one versus all is default in sklearn. And I think it's also just more widely used in all types of multi-class classification ML. So next, we're going to look at regression. And this is just like a simple slide showing some of the different applications of SVM. So as previously mentioned, support vector machines can be applied to classification problems as well as regression. For regression problems, we call it SVR. And I'm going to really just briefly touch on this. I've already been talking for quite a while, and I could talk for hours more just on SVR. So I'm not going to get into the math of it, just talk about some key differences between them, and then show you some kind of visuals and just give you an idea of what's out there. If you want to apply this, you're going to have to look into it in further detail. However, SVR isn't really used as much as, say, SVC. And then for regression problems, like the other like logistic regression or linear regression are more commonly used. So basically with SVR, we reverse our objective. and we aim to fit as many data points within our street as possible. So I'll show you on the next slide kind of how this is done. One of the parameters that I haven't spoke about, but which plays a large role in SVR is epsilon. And epsilon is a new hyperparameter that defines the area in which no penalty is placed on the training loss. So essentially, I'm going to go through it in a little bit more detail next slide, but it allows like a certain margin for like our points to be classified without any training loss. So like the larger the epsilon, kind of the larger we have that margin without loss. And then also it's important to note SVR, as with our nonlinear SVM classification, it doesn't really scale too well to like very large data sets. So if you have like a very large data set, you might want to look at another regression method. So here we can see that our definitions of our hyperplanes now have changed, and they include this epsilon. And again, this epsilon is the area which no penalty is going to occur. So essentially we can classify, like we can put our points right within this margin without any training error. So in this real world example, we can see that the data doesn't necessarily fit like tight in the margin. So in this example, changing that epsilon is going to change the shape of the regression. And we can see in the next slide that this can definitely play a huge role, especially in like nonlinear regression. And I'm not going to go into the math again, I don't have time. But if you're interested, sklearn's documentation is quite good on this. And then lastly, I just wanted to show these pictures. I like these pictures. We can see that we have our RBF, our polynomial kernels, and then a linear model. And we can see here that the RBF and the polynomial, they fit the data differently because of their different kernels. And we can actually see that here in our early time data, or in this data on the left here, we have like a tighter fit with RBF, whereas with polynomial, it's a little bit looser, more air. And then in our polynomial, we have like a tighter fit with our data closer to the right. So if this was time series, we could say, hey, maybe one's better with early time, one's better with late time. And that can be part of your factoring, or that can play into your decision on which kernel you use, depending on what's important for you in this regression problem. And like classification, your selection of kernels and hyperplanes largely impacts your accuracy, and your data will also dictate what kernel type and what parameter values are ideal. So next, I'm gonna go into a collab example.
Hayden, there's one question in the chat. Do you mind if I ask them right now?
Oh, yeah, perfect. Hopefully I can answer it.
So the question is, how is SVM used in the oil and gas industry, or what kind of tasks is it used for?
That's a good question that like I probably should know better than I do. I do know SVM is used quite a lot in the geosciences. So there's like a number of applications like seismic interpretation and, oh, I'm blanking, but there's a couple others where SVM is like one of the premier models for that. I also believe that it's used for kind of like time series data, like production, estimation, and the like. And as I previously alluded to, like when we're looking at regression, we can look at nonlinear regression as like most like oil field production would be. And then as far as just general applications, I'll get into that a bit later. But as a bit of a spoiler, it's used in like a lot of like machine learning, also like classifying types of like photos or text. And it's also used in medical imaging, as well as some like protein folding and a few things that I don't really understand, but apparently it's pretty good in that. So I hope that answered it.
Yeah, thanks, Hayden.
And then I'm going to go through the notebook here. Hopefully it works for me. And yeah, I'm doing okay for time. So SVMs are a particularly powerful and flexible class of supervised algorithms for both classification and regression. And again, they have other purposes, but these are the main purposes. And this is what and the classification will be covered in this notebook. So we're going to start with some like standard imports, Seaborn, NumPy, Matplotlib, etc. So we're going to talk about what really motivates SVM. And as Hassan previously talked about in the Bayesian and the naive Bayes classification, we learned that that's a simple model for describing the distribution of each underlying class. And it uses like a probabilistic approach, whereas for SVM, it's non-probabilistic and it's more like a discriminatory classification. And rather than modeling each class, we simply find a line or a curve that divides the classes from each other. And this can be 2 classes or many, many classes. So we're going to start with just like super simple example, similar to what we saw in the slides. And honestly, a lot of this is going to be like a repeat. But when I'm learning something, I really appreciate repetition. So I hope you guys do as well. So we're from sklearn, we're going to import this like make blobs. We're just going to randomly put these blobs. Really, the importance here is to show that this is linearly separable and that like we could eyeball a separation here. But how do we know it's perfect? How does it work in higher dimensions? So next we are going to just like fit some random lines here, just using the equation of a linear line. And we're going to put a point here, X, that we can talk about how we would classify. So we can see here that there's 3 linear lines that all successfully do separate the classes. However, we could argue that maybe like one of them is better than the others. And we can also see if we have X, that these linear lines are they're going to like estimate a different class. So if we look at this top one, well, we would consider this yellow. Whereas if we looked at this bottom one, we would consider it red. So next, we want to add margins to these lines to visually show the margins between these lines and start to like intuitively understand maximizing the margin. I think it's like an easy concept, but we should visually look at it. So here we can see now we have a gray margin. So each line has a margin that like touches each class of items. So we can see that this would be a support vector on this particular line. And we can visually see that the middle line has a much, much larger margin. So we could tend to say that that is a better classification for this problem. So if we actually want to use SVM, then to find the perfect solution for this, we can then use sklearn's SVM class, and we can import their SVC, which is just support vector classifier. Commonly, people just say SVM classification, SVM, SVC. Doesn't really matter. We can also see that we are setting the kernel type to linear, or as I previously mentioned, just no kernel type. We also see that we have like a really large C value. So if we run this, we see a lot of the defaults. We also see that C value and our kernel type. Not really going to go into the details there. Next, we want to visualize the decision boundary. So this is just some simple plotting. And what we see here is we now have what's looking like an SVM model that has maximized the margin classifier. So we can see here that this is what's referred to as like hard margin classification, where there is no misclassification. And we can see that there are 3 support vectors here. So again, as a recap, any point on the edges of our margin or within the margin are support vectors. And again, the support vectors are really the subset of the data that drives our minimization problem. So here we can run a support vectors. Sorry, I'm getting thirsty. We can look at the attribute of the SVC called support vectors, and it just shows an array of our support vector values. So just to confirm, we see like this one here, it's like probably 0.44, and then around like that 3.1 as we see here in this array. Pretty straightforward. So in this next line of code, or block of code rather, we want to talk about the kind of importance of this hinge loss function. And we want to visually show how the data points outside of the margin aren't impacting the optimal hyperplane. So we're going to plot 60 and 120 data points, and we're going to see that the optimal hyperplane doesn't change. So if we run this code, we see that, oh, I've actually changed this to 12,000, or sorry, 1,200. And we can see that we still have the same result, even with 12,000. So we can change this, yeah, to back to 120, and we'll have a really good idea. We see that we have one more support vector, but the hyperplane location really hasn't changed. If we increase this like very high, like say 120,000, 1.2 million or something, then we'll probably end up like with a point that would fall within the margin and would change the hyperplane. However, like I said, if we remove points out here, add more points, it's not going to change anything. Next, we're just going to look at an interactive version. It's pretty clear. So yeah, I'll just skip that. Then I'm going to talk about nonlinear SVM, because nonlinear SVM is really where SVM shines. And that's where a lot of our data in the real world sits. So when we combine kernels, as previously discussed, then we can project our data into higher dimensional space, either from a polynomial or a Gaussian basis function, or there's a few others. Those are the main ones. So now we are going to just import some data using make circles from sklearn, and then we're going to try and fit a linear SVC to this data. And we're going to see that it like pretty much fails. And this is like similar to that kind of question I had for everybody. Like, how could we use linear SVM to separate them? And we can see that like this does separate yellow from red only for like some of the points, and we have like a ton of misclassification. So how can we do better? So the next thing that we could do is we could create some function, let's say R, that is like a radial basis function, and we could use that. So at this point, this isn't the radial basis kernel, just a radial basis function. But we can see that if we plot that in 3D, we should see a, oh, sorry guys, I just noticed that this isn't really working. Sorry guys, I just gotta go to the GitHub. Yeah, this is the same thing. My Colab just wasn't recreating it. We see that with some radial basis function R, we have this separable data. We can create some hyperplane, maybe like 0.7, that separates the two. And then we have separable data. However, we just kind of created this function, and we got lucky that our data was centered. If the data wasn't centered, it wouldn't really look like that. It would look different. So that's like one of the advantages of using a kernel, because it is computing like the differences between all point pairs. It really doesn't matter the shape as much as if you just like threw a function at it. And also, as previously discussed, when we're using just like normal functions, what we're doing is we're projecting like n number of points into n dimensions, and that becomes like very computationally intensive. But if we use the kernel trick, we can do that transformation implicitly, And this is done without ever building that full n-dimensional representation. So this is why kernel tricks make SVM so powerful. And we're going to go into our sklearn and simply change the linear kernel to RBF. So we can do that here, and we can see these are just some of the defaults along with our C value we previously assigned. And also, we could also like remove this because SVC assumes a default RBF. So we can see like kernel RBF, that's going to be our default. So next we look at plotting that kernel function, and we can see that we now have a margin that's been maximized for this like non-linear data, which is really powerful. So now how do we tune the data? Because not all of our data is going to be like this easily separable, and it's not going to be what's referred to as like a hard margin. We're going to have something called like a soft margin where there's overlap, there's misclassification, all that real world data stuff we're used to seeing as data scientists. So yeah, we're going to make a blobs here, but we're going to add some clustered standard deviation here. So they're like mixed together. And then we're going to talk about this like C value that I talked about previously, the hyperparameter C. And the way that it's defined here is that it's like a fudge factor that softens the margins. And the way I like to think of it is like it allows misclassification for the purpose of maximizing the margin. So here, we're going to look at like two extremes where we have like a large C value and then a small C value. So with a large C value that's really punishing the misclassifications, we see that we have like a very, very small margin. And with a very like a looser C value or a lower C value, we have like a much larger margin. And we can see that we're still classifying these well. We're just including more points within our margin. So we have like a lot more support vectors. However, if I was to like increase this cluster standard deviation, let's try 1.5 maybe. I don't know. We'll see something where there is misclassification. So for this example, we have misclassification in both. However, we still get like the larger margin here with a lower C value. And then I just want to quickly do this before I move on. Let's try and throw in even a larger C value. It might take a bit to compute here. Let's see, I've never done this. Yeah, like we may even need a much, much larger C value to tighten it, or this could be as tight as we're going to see it. Anyways, as I like talked about in my presentation, like any ML model, we really want to like tune these hyperparameters to like find that happy medium between over and under fitting. But it's really important to understand from a kernel perspective, if we're using RBF and if we're using like polynomial or sigmoid, you can't just tune one of the parameters, gamma or C. You got to tune both of them. In this example, I only went through like the linear kernel and the RBF, but we could have did the same with a polynomial. So next, there's this facial recognition example. So I'm going to skip this and Hassan's going to come back. It's a neat example, but I've never dealt with picture data at all. I've only dealt with like more numerical or classification data. So he's going to come back to this because I don't know if I'll do it justice. And then lastly, I'll just go through like a bit of a summary. I know I've like talked about a lot, but once you start looking into SVM, you realize it's like a huge subject and it's a really important model. It's probably one of the more commonly used ML models. So again, the dependency of our models is only on the relatively few support vectors, which means that like this is very memory effective. And then also because we are only looking at points near the margin, this works well with higher dimensional data. We can even use like on data that has more dimensions than samples. And that can be an area that this would outperform other models. Again, kernels make this very versatile. But there's also disadvantages like anything in life. So the scaling with the number of samples n is O(n) to the power 3 at worst, or O(n) to the 2. So this is big O notation. If people don't really know what that is, don't worry, I didn't either. It's based on like a computer science definition where it tries to, and I hope I don't butcher this definition, but it tries to basically relate the complexity of the computations and like the storage intensity of an algorithm to some scaling factor, in this case, the amount of samples. So as we increase our samples, we are becoming more computationally expensive to like the second or third power, which can cause huge issues if we have large data sets. So again, nonlinear classification regression doesn't really work above, say, 50,000, maybe even 10,000 observations. And then, yeah, the next ones I'll just talk about in my slides. So quickly, some of this is going to be a review maybe. Some of the advantages here are that it's like an easy to implement model, not many hyperparameters. It's easy to understand and it's powerful from a baseline perspective. Yeah, again, there's few hyperparameters, therefore less tuning. So maybe easier to use than other models. It's memory efficient because of the kernel trick, and also because we're dealing with subsetted data because of our support vectors. We also are using kernel tricks. I could talk a lot about that. I already have. Lots of advantages there. And it's also versatile in the types of data we can use it on. We can use like photos, we can use text, we can use numerical, etc. We can also use it to like very high dimensions, 10,000 dimensions, whatever you want really, or not whatever, but a lot. And we can also use it for like many, many classes, as I went over in the multi-class SVM. So disadvantages. So the disadvantages are that mapping data to a higher dimension could lead to overfitting the model. We also really like our results depend on our hyperparameter C. So that puts a lot of onus on like the ML user to like select the right C value. And also the kernel selection is like very important. So you'd want to like do cross verification to make sure that you're using the right kernel. And then also it performs like poorly on very noisy or very large data sets. I don't have the exact number, but I've heard anywhere from like 10,000, 50,000 observations with like 1,000 to 5,000 features might be kind of on the edge. But I haven't really used this model. If somebody has more experience, they could speak up. And then also it requires balanced data. So a balance between the positive and negative cases. Lastly here, I think I've almost been talking for an hour, but I'll talk about some of the applications. So again, like this is a huge topic, hence why I'm talking fast and going over a lot. To do this topic justice, you need to like discuss a lot because it's so powerful. And some of like the general uses right now is facial detection. So we can use SVM to like determine in a photo which pixels are a face, which aren't. We can also do text and hypertext categorization. So this would be, hey, is this business or entertainment? And then handwriting classification. We can do this for signature verification. As many of the world's working from home right now, that's quite important. And medical cancer classification. Is cancer, is not cancer from imaging data, very important stuff. And then lastly, protein remote homology detection. So I had no idea what this was. I honestly still don't understand it, but apparently this is like a very complicated medical problem and it's a very important one. and SVM performs like well above any of its competitors, and it's like the go-to algorithm for this particular problem. So I found that cool. That might be a bit of a tangent as I don't understand it, but anyways. And then, like I said, there's like oil and gas applications, geotechnical applications. Honestly, the list goes on. And lastly, is there any questions?
So there's no question in the chat, but I have one. So you mentioned about the kernel tricks, and there are different functions there. So what do you recommend if we want to learn more about those different types of kernels and how we can apply them?
Yeah, so that's a really good question. I would look at sklearn's documentation, and that's where I got some of my equations from. That's going to just give you an idea of like how to use the kernels, and then it talks a little bit about the differences between the two. And then Andrew Nang's goes through like them in two of his videos in his machine learning course on Coursera. And then additionally, this is like a math topic as well. So there's tons of information on the internet and in textbooks. And honestly, I probably didn't read about this as much as maybe I could have. It's like a pretty abstract math theory. So, but it's really interesting. I'd recommend everyone read into it, especially if they're going to start applying SVM. It's super important to understand.
Thank you.
Awesome. Oh, sorry. I kind of talked over you.
I don't see any other questions in the chat, but.
Perfect. Well, I really appreciate the opportunity to speak to everyone. I hope somebody learned something that will make it all worth it. I know I learned a lot. So from a selfish perspective, it's already been worth it for me. So yeah, I'm going to pass it off to Hassan, and he's going to go through that imaging question in the notebook, or the imaging example, and then he's going to teach us about KNN. Thank you, guys.
Thanks, Hayden. That was really good. I'm wondering if I think I should go through this, and then we'll maybe go on a break. Quick break. Let me know if you can see my screen.
Yeah, we can see.
Okay, cool. All right, so this is just a straightforward example in SVM here, where we just pitch this data from sklearn. So this data is basically people's faces, which we'll see in the next. And from this data set, we want to just get the people that has a minimum of 60 faces, basically, in the data set. So, and then here we're printing what we got from the data set. We have the people that have a minimum of 60 faces in that data set. These people, and then we're getting the shape of the data. And here we could print the overall features of the data. So the rows we have in our data set now, it includes 1,348 rows, and then would be the columns, the features would be close to 3,000 features. And this is just to see like what the features look like, what the data looks like. So as we can see, these are features of images. So these are pixel values, and it would range from 0 to basically 0 to 255. And here we just want to like print out using which library we're using. The matplotlib, we just want to print and see like how the data looks like actually, because it's image data anyways. And each one with its target name. So again, the data set includes 3,000 features basically. And what we want to do is we're not going to use all these features into training our model. So we do something like PCA, perceivable component analysis. And what this does to us, to our data, is to basically, we do that to reduce dimensionality and get the most fundamental components. And actually, we decided how many n components we want, and we set that for that to be 150. that's just another arguments for the function, and for random state, that's for reproducibility. And we create we initialize a pipeline where we could throw our process data, and after we put it through the PCA, and then we put our model that we initialize here with the kernel RBF kernel that Hayden explained previously, and with a class weighted balance. And here we just use sklearn again to pretty much reason sklearn for everything. So we split the data to train and test. And we use something called grid search cross-validation. And this is when we want to get try to get the best parameters, hyperparameters for our model, so we could actually use it to get the best performance. And when we do that, we could actually print out. So we could give it a list of, and just to know that these are actually, the more data you have and the more like parameters you have, you wanna test on, you want to perform grid search, it's gonna take more time, so it's more expensive to compute. But in this case, we just pick for C and gamma, each one a list of 4 hyperparameters. And then after we do the grid search, we cross-validation, we print the best parameters. So here, C parameter gave us 10, and the gamma parameter was 0.001. And actually, the time that was taken here is almost a minute. Okay, so what we do is we want to basically fit our model with these best parameters. Sorry, we want to use this we want to predict with using these best parameters. So we actually use these and to build the model again. And this test set here, we didn't actually touch it to cross-validate our, cross-validate. So basically the model didn't see these data yet. So that's what you want to make sure you do when you do cross-validation. And I'm actually going to come to it in KNN a bit, because we use it in a lot of different models as well. Okay, so here we're actually trying to visualize the output. So after we predict, we print out the images, and each one with the predicted label to it, or the name of the person. And we could see here, we don't want the misclassified, we just print it out in red. And then we could see that according to this, we have, I think here, this is George W. Bush, was misclassified as Blair. And this is what I actually wanted to print when I was presenting earlier, and I put it on the Slack channel chat. And it's basically, before we were printing the confusion matrix, and I just wanted to print this report where you could see actually the performance of the model per class. And the overall accuracy, we could see it's 85. So that's how good a model we have right now in this data set. And I just got these from Wikipedia, basically. So basically, the precision, it's just like definitions of a precision recall, if one's clear. Sometimes it depends how crucial you want or it helps you. Not always, you don't always want to be looking at accuracy, right? Like sometimes if your data is imbalanced, accuracy is not the best measure for your model. So you want to look at precision recall. And I actually, he explained, I'm just going to read it out. So the precision actually answers the question, how many selected items are relevant in our data? For example, if we take something like Blair, for example, so it tells us what proportion of images we detected as Blair actually were Blair. That's the logic behind this, the precision. And then for recall, it answers the question, how many relevant items are selected? So again, going back to the Blair label, which tells us what proportion of faces that actually were Blair, they were actually detected as Blair. So yeah, every time basically I print out confusion matrix from a model or a report, I always kind of go back and read these and make sure I understand them. So I don't feel that they stick a lot in my head, but yeah, And the F1 score is basically a combination of the precision recall. And this is actually a good measure when your data is imbalanced and to use instead of accuracy. And this is again the confusion matrix that we saw earlier. So we could get a sense of how the models perform and where it's actually confusing labels with the true label. Again, going back to Tony Blair here, you could see the predicted label here sometimes differ than the real label on Tony Blair. So it actually misclassified Tony Blair by Donald, this person here at some point at one event. So yeah, I think this is what I wanted to go through quickly. And if there's any questions,
there's no questions in the chat.
Okay, let's go for, I think, what do you think, 5 minutes again, and we'll come back?
Yeah, I think 5 minutes will be fun. So we can probably come back around 3:18.
Okay, sounds good. All right, I guess we'll begin about talking about KNN. All right, so where does KNN sits in the hierarchy? So it's a non-parametric model that can be used as a classification or regression algorithm, and it's included in supervised learning. Although it could be used for regression and classification, I think it's mostly used for classification. Yes. Okay, so first, maybe not to confuse this algorithm with the k-means algorithm, which you might have heard of. Basically, the k-means is a clustering or unsupervised algorithm, which I think might be covered next week in the last session. So anyways, KNN uses k nearest points or nearest neighbors for performing classification. So basically, if it walks like a duck, quacks like a duck, then it's probably a duck. You could basically classify everything like that. Just kidding. So the k parameter plays an important role in the decision of what class or value our testing record will belong to. So k is basically the number of nearby points that the model will look at when evaluating a new point. Okay, so it's good to know this about KNN, that is a lazy learner. So it's an instance-based classifier. So that means that the calculation are only done during the prediction phase or the testing phase. Unlike other traditional classification models that represented earlier, which by here depicted by the figure on the left side, they're called eager learners. So for instance, like decision tree, for example, and other models we mentioned already. So the model in KNN is the data itself. So there's no model being constructed from the data itself. So depicted here on the right side. So this model basically has, that's why basically has no loss function that can be minimized during training. Since the only training that happens to KNN is memorizing the data. And this is kind of a disadvantage, but we'll come to that. So eager learners commit to a single hypothesis that covers the entire instance space. So to the model construction, eager learners take a long time for training because we usually perform optimization where the function is being fitted to the data using something like gradient descent, and therefore it takes, after that, when you want to predict, it takes much less time. So that's why in KNN, classifying a new record is relatively expensive, which is why we need to structure and for a structure for retrieving the nearest neighbor very fast. So this is called the nearest neighbor search problem. So in a classification scenario, the object being assigned to the class that is most common among its k nearest neighbors, where k is a positive integer. typically small f k equals 1, then the object is simply assigned to the class that single nearest neighbor. So whereas in a regression scenario, the object value is the average of the values of the k nearest neighbors. So in this figure, we can see how data selected in our training around our neighbor or the test record is basically based on selected k, and therefore the common class is changing. So here we have on the left, we picked k as 5. So the common record here is the common color between the points that have been picked is blue. So we could classify the new record as blue. However, here on the right side, if we took k as equal to 9, then the more white points will be picked, and then the common class would be white. So k, next, yeah. So KNN requires mainly the following parameters. So the set of stored sample records. And the value of k, the number of nearest neighbors to retrieve. And finally, we want the weights for the neighbors, as each may contribute different weights. For example, the further sample, the smaller the weight will be for that sample. Or we could keep it as a uniform weight, of course. So to classify a new record, we compute its distance to other sample records in the training set. And we identify k nearest neighbors, those with the minimal distance to them. And we use the common class or average value of nearest neighbors to determine the class or value of unknown record. So say that we have our data, and now we want to establish a distance metric. So as a user of this algorithm, we must know meaningful distance functions. So there are many distance functions available for KNN. But keep in mind that choosing the distance functions that can affect the classification accuracy for the KNN classifier. So for example, I put actually a link here. So I'm not going to go over the chi-squared distance function, but it's talking about how in the medical domain, a data set including categorical, numerical, and mixed type of data, the chi-squared distance function performed the best. The model gave best accuracy when using that distance metric compared to other distance functions that are mentioned here. So let's look briefly into these ones. So the most widely used is the Euclidean distance function, but it doesn't always give the best result. And by default, I think it's actually set in sklearn. If you want to use KNN, it's set as the Euclidean. But I'll show you in a bit how it's set. And note that the most of these metrics require actually the data to be scaled, and that's a crucial part of this. So we could use these functions to compute the distance between the 2 points in a feature space, where k is the dimensionality of the feature space. So the default metric, as I mentioned, is Euclidean, but if you go to sklearn, and you'll see that in the documentation that Minkowski is the default one, but the free parameter, where here it's depicted by q, which is there in sklearn is p, the power parameter is equal to 2 by default. So that actually falls back into Euclidean. So that's how it's actually used by default. So when you set the q for 2, you're using actually Euclidean, and if you set the q or p to 1, you're actually using the Manhattan. So yeah, as I mentioned, the Euclidean is the most natural distance function that used for numeric attributes. So basically, you take the difference between the testing and the training values for attributes. Attribute k, square it and add it up. And this function is symmetrical and treats all dimensions equally. However, it's very sensitive to extreme differences in a single attribute, because if there is a big number in difference, it will get squared and it will be large. Okay, so this is a simple example showing how we could use the Euclidean distance function. So we have our data set with two features. Let's say we got, this is, let's say, a fake bank data, and it's about the status of our customer. So let's say this is the customer names and their ages and the loans. And if actually by default they got a loan, or yes or no, Y stands for yes and N for no. So we have a new customer and we need to predict his status by using the Euclidean distance. So what we do basically is we calculate distance for all the data points. So for example, the distance between a new record here for Andrew and the first record, John, here on the top, would be the square root of 48 minus 45 squared plus the 142,000 minus 40,000 squared. All these are square rooted. And here we are taking in this example k to equal to 5. And when we take the k equal to 5, we see that two of these nearest neighbors, the 5 nearest neighbors, defaulted to no and 3 to yes. So what we conclude is that Andrew default status is yes. Very simple example using Euclidean. So we saw which distance functions we could use for numeric attributes. Now when we have, what if we have categorical variables? And what do we use? So we use the Hamming distance function. So it basically, we look at each attribute and we check if they are equal or not. So if they are equal, then this formula is a 0. And if not, it computes to 1. We basically count how many different attributes there between two instances. And I think that in sklearn, if you want to actually use that, you could set the p parameter to 0. I think that's how it's set up, but you could check that out there in documentation. And if you set it to 0, then actually you're using the Hamming distance function. Okay, so we have our data and we have established a distance metric, but what about k? We saw that k, using different values of k, we could get different predicted class overall, or a value. So it's very important, and choosing it is very deterministic and has effect on our algorithm as it controls the shape of the decision boundary. So how do k? Well, there's no one single value that k that works for every data set for k. So what that means is we have to investigate the data on hand. Usually in binary classification, an odd value of k tends to work better because it prevents the algorithm to run into a tie. For example, looking at the nearest even number of points, like let's say we have 4 points, and we find that each one belongs to one class, so that's a tie. Sorry, each 2 points belong to one class, so that's a tie between two classes. So increase in k tends to smooth out the decision boundaries, so it reduces the noise on the classification, which will avoid overfitting, which is good, but that's at the cost of the resolution, because now our boundaries within our feature space are less distinct. So we could always further inspect and learn our data to choose an optimal k, but usually we perform cross validation to determine a good k value. In this example, this figure, we could see actually how a large k has smoother decision boundary, which means lower variance but increased bias. And we could see here it's less distinct boundaries. So if you visit, I put this is the source of the figure at the bottom here. And in that source, under that figure, you could see it actually links to more information about bias variance trade-off. So you could go and read about it. It's worth it. Okay, so cross-validation. Since this is very important, we saw already that we use in different algorithms to pick best parameters. So this is what we're going to use here to get best K. So in general, or most commonly used here is the K cross validation method, or the K-fold cross validation method. And the K here it's not related to the K in KNN at all. So this method allows us to estimate the test error associated with the learning method in order to evaluate its performance, or to select appropriate level of flexibility. So as we can see here, the training set, it's split into 5 smaller sets. So this is our training, this is all data, and then we split it first to train and test data. The test data we don't look at until the final evaluation. And this is, we start splitting our data we split it here into 5 folds. So the model is trained on K-1 of the training sets. So in each loop, it's trained on K-1. So because we have K equal 5, so then we have 4 data, 4 folds that the model will train on, and it will validate on each time on the one fold that was left out. So we have 5 loops. So it's repeated K times, basically, generally speaking. And the performance measure reported by K-fold cross-validation is then the average of the values computed in the loop. And best parameters can be used to get better performance on the testing data. So again, this test data, we don't use it when we do cross-validation at all. The model doesn't see it. So that's really important. Okay, question alert. So just based on this information so far, let's say we did cross-validation and we got this graph out of our cross-validation function. So in this graph below, which would be the best K value to pick for our KNN algorithm? So, chat. You could put your answer in the chat, which I can't see for some reason.
Yeah, there's answer is 2, 25.
It said 25.
And someone answered about K equals 7, 7.
Okay, cool. You guys are on the right track, but it's 7. But I understand because these are really close at the bottom here. So I was going to put lines, but that would have gave you a hint. But anyways, yeah, 7 is we get the least error in our cross validation. So good job. All right.
Can you explain why?
Because we get the least error when we do. So basically, in this case, the least error we got is when K was about around 7. So that's why we deduce that K at 7, the model is performing the best.
Sounds good. Oh, there's another question related to the distance function, I think.
Okay.
So it basically, so Julia is asking, when we have a unbalanced data set, would that affect to how we choose a distance function? So basically, what's the impact of the data distribution on the selection of distance functions?
Yeah, so there is impact. There is so this is what's important to know, and to know your data, because for example, if you do your distance here between, we didn't scale our data in this example, but when we did the Euclidean, if there is a big difference like this, we get some features would have more weight on it than other features in normal. So we have to be careful. In this case, do we want more weight, for example, from the lone feature than the age feature? So we gotta be careful. So in this case, we didn't scale our data, but it's important to scale. This is kind of an overhead in this algorithm when we use distance functions. Does this answer your question?
Yeah, I think that's part. He also asked about, like, for example, if we have more positive labels than the negative labels, so the data is unbalanced. Do we need to think about choose different Euclidean distances to deal with such unbalanced data set?
That's a good question, actually. I'm not sure if we could, what other measure we could rely on if we have imbalanced data, but I would say in this case, it's important probably to have a balanced data set. And there are ways to balance our data in case we don't have balanced data. So I think it's important to actually do analysis in our data first to know. I think that's actually important as well, part of it. But I'm not sure which, if we have any distance metric that could take care of such thing.
Yeah, I think I personally don't know if any of those distance can help with the unbalanced data set. But it's a very good question, though.
Yeah. Okay. All right, so basically we got data, distance metric, we figured out K. We finally want to pick a weight parameter. So we want to basically decide here. So we could either decide by either if we want uniform or distance. So uniform weight, basically using uniform weight, that means each point in the neighborhood is weighted equally toward the decision of the classification. Whereas a distance, in the distance weights, points are weighted differently, which is by the inverse of their distance. Where closer points will have greater influence than points that are further away from our testing ring. And this is also built in, it's hyperparameter built in sklearn. You could pass it in. I think by default, it's a uniform. I just added this actually figure very late, but it's from the documentation of sklearn, showing uniform on the left side versus weighted on the right side, weighted selection of neighbors. So what's it? Like to see, like try to eyeball the differences between, if we pick having the same K, of course, how much difference we could eyeball or some between these two figures, one we choose weight as uniform or weights as distance. You might want to experiment with this actually when you apply this algorithm and evaluate based on the accuracy on the model. So maybe again, as like how we saw with what we did with K, do similarly here with the weights and see where the model performs better on our testing set based on different weight measures. Okay, I'm gonna jump into the notebooks, and I think after that I'll come to the advantage disadvantage, and then we'll be done. I think we really covered all the time here. Sorry if we're really taking so long here. Okay, so in the notebook, we'll go over like some code basically, and basically it is a comparison between KNN and other decision tree and random forest. There's random forest also comparison there. But we've pretty much gone over a lot of this material that's here on the top at the beginning of this topic here in this notebook. So we talked about K, we talked about the a lot of this, like which parameters is required. These are also other hyperparameters. These algorithms I didn't talk about, but these are optional, and you could read about them in documentation. There is actually more there to learn about. I would say it's like how you choose the nearest neighbor in a way. It's different than the distance metric we talked about. Okay, so this is a cross validation. Okay, fault cross validation, and we talked about already. So this is okay. Now we're going into examples. So in this example here, we what we did is we downloaded the this data for telecom churn. So and this data is about customer churn prediction. So what we did is we we do pre-processing. We factorize these two features, which are international plan and voice mail plan. What this actually does is from pandas, as you can see here. And actually, I open it here already. No. So what this does is gives you two outputs. The first.
Oh, Hassan, are you sharing? I think we can't see.
Oh, sorry. How did that? I noticed something, but I didn't know if I stopped sharing. Still working?
Yeah, we can see it.
Okay, sorry about that. So I think I clicked here by mistake. It's very close. Okay, so what I was talking about is what we're using here. So we're using pandas to factorize these features. And what this does is, see, so it returns when you run this function, it returns codes and uniques. So if you have something like this, categorical variables, it returns the first variable return is the array of the codes. So it understands, it knows which one is the same, and then it gives you like numbers instead, basically. And then the second variable is the uniques, which is gives you the unique item in that column, in that feature. And if you set sort to true, you actually, as you can see here, B was 0 and then A was 1 here. If you just want to set it to, when you want to sort it, so and then A becomes 1 and then B becomes no, sorry, B becomes A becomes 0 and B becomes 1 and C becomes 0 and so on. All right. What we did here again is we actually set the data type for churn as int, and we actually use that data to be our label. So we drop it. We drop state here. In this example, I didn't put this together. I'm just going over it. But in this example, they mentioned that they dropped state, but there wasn't any further thing about why they dropped state. They just want to see if the models. You could try yourself, import this to a Colab and see if the model performs differently with the state, given a state feature. Okay, so we print the head. It's always good to see your data. And in the next cells here, what we do is we want to split our data. So we split to 70% training and 30% testing or holdout in this case. And we build two models. So we want to compare between decision tree, in this case, and the KNN we just talked about. So for decision tree and KNN, we don't do any cross validation right now. We just give them the hyperparameters we think they're going to perform good. So for decision tree, we gave a max depth of 5, and in KNN, we give the nearest neighbor of the K basically to be 10. And we fit the decision tree. And then we, we need to scale the features for KNN, and we do that in this step here. And we use a standard scaler to do that. So it's very easy once you start working with these libraries. You just basically want to know which classes to use to do that. And that's it. So our accuracy score basically from our decision tree performed, our decision tree performed much better than our KNN. So our decision tree gave 94% accuracy and our KNN performed at 9%. And this is before tuning the hyperparameters for each model. Now let's perform cross-validation. So we use the grid search for cross-validation, and we give the fold 5 folds. This is for parallelization. So basically, you just parallelizing the job. As I mentioned, this could be very expensive because it depends on how much you're given to check between, how much is in the list. So if for our tree here, we give max depth of range between 1 and 11, and max feature range between 4 and 19. So I think it's important if you have computing power, it's important to use this as -1, so you get it very fast. Verbose true is to get more output, I guess. To could read more about what happened, and we fed it. So for our decision tree, after that we could print out the best params, and you see that your best max depth is 6, and max feature is 17. And here we actually, before we didn't even set the max features, but we have set the max depth to 5. So actually it tells us that max depth to 6 actually would perform better. So we would see, we print the best score based on these parameters for this model, and gives us 0.94. So it's pretty much, treat the best score, and then we do it on the holdout set that we didn't do cross validation on, and give us 0.946. And this is just printing out the tree. You can traverse through it and see, but I think it's too small. Maybe you need to zoom in to see anything in here. So anyway, so what we do is now we want to do cross validation for our KNN model, and we want to see if it performs better or not. So in this case, we initialize a pipeline, and we pass through it. We want a scalar standardization and the KNN classifier model, and this is KNN params. We want to give a K from range from 1 to 10, and when we do the 5-fold cross validation, again we use the same params here. We pass the pipeline and the KNN params, and we do 5 folds. We fit it, and we print the best parameters out, and we see that best K for best model is 7, and accuracy score actually doesn't go up by a lot. So I think just stayed about 89%. So here the tree proved to be better than the nearest neighbor's algorithm. So the decision trees perform very well, and even random forest, let's think of it for now as a bunch of trees. Yeah, we learned about it previously. So in this example, random forest cannot achieve much better performance. So actually, decision trees here perform the best. Random forest gave accuracy about 0.94. And here for random forest, we actually we do our cross validation to get the best parameters, and then we use actually after hyperparameter tuning, we get up to 95%. But decision trees is still got higher than that. This is, I think, another complex example for decision tree and KNN. I think here we just gave us a very random data set, random points, but we wanted to have this linearly separable data. And we see that actually decision tree kind of suffered a little bit trying to predict here. So we could see here, although solution is just a straight line, we could see that decision tree have kind of struggled throughout this. But if you actually use KNN for that, you actually get better performance for KNN. Again, it's better to open this in a collab. I just didn't want to do that. Don't want to break things. Okay, so decision trees and KNN on digital recognition, MNIST handwritten data set. So this is another example, basically comparison. So we're going to look at these two algorithms, and this is kind of a real world task. Very close, I would say. So we'll use sklearn to load our data. And it's an example where KNN actually works very well. So the picture is 8 by 8. And similar to the same thing we saw with the face recognition there, you could print the same thing and see the shapes and all that for the data. And this is just some more visuals for how the data looks like using Matplotlib library. So let's do the same experiment as the previous one, but let's change the ranges for tunable parameters. So we split our data and we build a pipeline for first k nearest neighbor. Actually, first the tree here, you see that max dip to 5, and then the KNN with the k equals 10 for KNN. We fit the data for both models, or other way around. And what we get here is so accuracy. The KNN actually, this is the KNN output accuracy, and this is the decision tree. And our KNN, as you can see, perform much better than the decision tree on this data set. So if we want to hypertune the parameters, so if we give our decision tree for the cross validation, we pick max depth of this list. It's just going to go through and see the best performance on the training set and this max features. And when we do that, we fit, and actually with these the parameters or range of parameters, we get the best would be about max depth about 20 and max feature about 64. And on our, so I'm just going, okay, now here. So actually it went above, so, but not still, even with tuning hyperparameters for decision tree, we still don't see it going higher than the KNN, what KNN performed before actually tuning hyperparameters for KNN. So basically this is just, and here we actually also, after we tuned, I think our KNN, we do hyperparameters and we get the mean, we get actually even better performance. And then for random forest, we do similar thing here. But this is basically a final output between the 3 different models and their performance. So basically what this means is for decision tree on in our cross validation on the training set, the accuracy was 84%, and then the holdout, the testing accuracy was 84%. KNN on the training set accuracy was 98%, 99, where in the testing set it was from 98, and then the random forest 93% on the training set, and then the testing set performed 94. So you can see that actually KNN performed much better than all other complex models. I think this is another last example here for KNN, where I think there is a point of this doing that. Oh yeah, so this is showing the flaw in KNN, where it's kind of complicated case where KNN actually doesn't perform well, because what we did is one of the features, we actually made it proportional to the target. So actually, if you want to train your model, if your model learns properly, it should actually, the prediction should be like 100%. If you have that, it's basically training. Your features basically one of the features in the feature set. It's still in the right prediction pretty much. It's a proportion of the right prediction. So this is what what we did here, and this is what we're gonna try to see if actually KNN catches that. And for some reason, it didn't catch that. because it's not a complex model, but the accuracy was still high. However, it should have been basically 100%. Because if we actually train a decision tree right away, we could see actually decision tree performed 100% on the cross validation and 100% on our training set. So you could see how this is a flaw in KNN, and this is why it's not considered as a complex model like other models. So decision tree actually was able to learn that, oh, well, this is a proportion, this features portion of the target. So I learned now, I know how to predict properly. We just basically multiplying with this fraction. Okay, I think this is it for this notebook. I think I'm gonna just go back quickly here. And almost done, just 2 slides about advantages, disadvantages, and we'll be done. Okay, so the advantages of KNN. So there's no training period in the KNN. So model has the data in KNN model. So the data itself is the model, which will be a reference for future predictions. And because of this, it is very time efficient in terms of improvising for a random model and on the available data. So KNN is very simple to implement, as the only thing to be calculated is the distance between different points on the basis of data of different features. And this distance can easily be calculated using distance formulas such as the Euclidean, as we saw, or Manhattan, this function. So as there is no training period, therefore new data can be added anytime since it won't affect the model. So since this algorithm relies on distance for classification, normalizing the data can improve its accuracy dramatically. So this is very important. And handles multi-class cases. I have, I think, a lot here and disadvantage. So it doesn't work well with large data set because we're going to be calculating distance between each data instance, and that would be very costly. Minimal or basically no training phase of KNN comes with both at a memory cost, since we must store potentially maybe a huge data set in memory, as well as a computational cost during the test time, since classifying is given observation requires a rundown of the whole data set. Practically speaking, this is undesirable since we usually want fast results. So trying to find the best case is time consuming over a larger data set. So you want to maybe you want to parallelize, make sure you parallelize the process, use all processors you have in your machine. Does not work well with high dimensionality, as this will complicate the distance calculating process to calculate distance for each dimension. So this is sensitive to noisy missing data. So it could produce different distance measures. This is actually important. I'll go back on this again. So it could produce different distance measures from the same training data computed before and after normalization. So you got to be careful and know when you want to normalize and when not, which not a good sign for robustness of this algorithm. So basically, attributes may have to be scaled to prevent distance measures from being dominated by one of the attributes or another, which I think we talked about earlier. So data in all dimensions should be scaled properly, because in real-world problems, for example, in banking, if you have features such as age along with mortgage, as we saw, or loan, those features have very large distance between them. Again, this is also talked about. So you want to know which features you want to scale, because it's very crucial to the output or the performance of your model if you don't scale properly. And training applications. So usually KNN is used in search application. We're looking for similar items like document concept search. very popular in recommendation systems actually, and also used in medical sectors, like finding diabetics ratios, and so on. So I think the last, actually, this would be our last slide for today. So as we saw, there's a wide range of supervised learning algorithms that are available. So each with its weaknesses, strengths and weaknesses. So there's no single learning algorithm that works best on all supervised learning problems. Sometimes best approach is to try and run multiple different models, but don't forget to know what the data looks like before doing that. Basically doing some preliminary analysis on the data is very crucial. So I'm gonna end it at that. I would like to thank everyone for listening, and my partner Hayden, I think you've done a really great job today, and everyone already that participated in this bootcamp, and for the GG community. And don't forget to continue asking questions on the Slack channel. And thank you everyone, and happy learn. And if there's any questions, I could take them in right now.
No, there's no questions. But I just want to shout out to Hassan and Hayden, and I really like your conclusion slide that I think that talks about the necessity of having this bootcamp, because we need to keep learning different algorithms and what's the advantage and disadvantages, and also apply them to various problems. And I would like to thank you all for participating. And if you have any more questions, please post on the Slack channel, and have a rest of your night. Looking forward for our last lecture next week. Thank you.
Thank you.